Okay, our next video is our second learning target in astronomy, and this is about sun activity. And this fits in, this is our second learning target of our unit. We talked about galaxy formation, and after this we're going to talk about how stars actually form. But for right now we're going to focus in on activities on the sun and how they make different elements and how we know that from here on Earth. So our goals for this learning target are to explain events that happen on the sun, like sunspots, solar flares, and solar winds, relate events like auroras and power disturbances on Earth to sun events, and explain the process of fusion, how it makes new elements, and how those elements get spread across the universe, and also how we know that. So these are sunspots. These are dark, cool spots on the sun. But they're not really that small. Some of them are, way bigger than planet Earth and way bigger than, or as big as Jupiter. And even though we call them cool, they're still thousands and thousands of degrees. So it's just relative to the other parts of the sun. So why do we care about sunspots? These temporary dark, cool spots on the sun, they're caused by a change in the magnetic field of the sun, and it gets super complicated, so we're just going to say that something inside of the sun is changing, and that kind of works its way out of the sun, and it causes sunspots as it works out. And one of the things that it makes, something called a prominence, which is a bright gas loop of plasma that extends out from the sun. So the sun is made of plasma, so this is also a plasma loop. So think of it as a rainbow made of plasma. And this loop here is quite large. We could fit Earth easily underneath, and if sometimes they're big ones, we could even fit the largest planet, Jupiter, underneath. So we care about prominences because often a prominence can start to twist, and just like a rubber band, if you twist and twist and twist and twist, it will eventually snap. And when it snaps at the end, it's going to jet out plasma into space, and that could be directed right at Earth. So a really large solar flare is what we call a coronal mass ejection, or a CME. And so that's a giant cloud of plasma that gets ejected into space. So as those particles that get ejected from the sun fly through space, we call those charged particles flying through space solar wind. Just like wind on Earth is our atmosphere moving around, particles in space moving around would be solar wind. So the farther away from the sun that you get, the less solar wind there would be. But luckily our planet has a magnetic field, and the magnetic field does a pretty good job of protecting us from the solar winds that come from the sun. But one thing that does happen at the North Pole and the South Pole, the magnetic field, that's where it emanates from Earth, and so it's kind of, think of it as like a weak spot in our magnetic field. So some of those charged particles can break through the magnetic field in one spot, and then they can work their way back to the Earth. And when those charged particles hit our atmosphere, they glow. And depending on what element they hit, if it hits nitrogen or oxygen or whatever, it's going to glow a different color, just like different elements in a neon light glow different colors. So auroras, or the northern lights, are glowing particles of our atmosphere that interact with the solar wind that comes from space. And there's a couple good YouTube videos if you want to watch what they actually look like. Sometimes pictures don't do it justice. So we're concerned about all of these things, so sunspots all the way to solar winds hitting our planet, is because it could make a geomagnetic storm, which is a temporary disturbance of Earth's magnetic field caused by a shock wave of solar winds. And we're worried that those shock waves, if they're strong enough, they could disrupt satellite communications. They could disrupt airplane communications. But the biggest thing that we're worried about is our electric grid, which acts as like a giant net to maybe capture those charged particles from outer space. Those are susceptible to transformers blowing up. So the charged particles hit the lines, ride the lines. Then there's a surge of energy going through the transformer, could potentially blow it up. So we could potentially be without electricity until those transformers are replaced. Which, if it was one transformer, wouldn't be a big deal. But if we got hit by a very large CME and it was a direct hit over North America, we could potentially be without power for an extended period of time until all those transformers got replaced. So that's one of the big things that we are worried about. Just to put it in perspective, when we talk about solar flares or CMEs coming off of the sun, they're gigantic. They're much larger than the Earth. And the average solar flare isn't very big, but every once in a while we get a really big one. And the one in 1859 was a gigantic solar flare, and it was so gigantic that the only electrical grids that we had at the time was actually just a telegraph. It was just one wire connecting two places, but there was so much energy running through those telegraph lines that it caught the telegraph machines on fire on either end. So we are, obviously way more dependent on technology and electricity now, so we could potentially be in trouble. So one of the things that we looked at the beginning of this learning target was sunspot cycles. So we know that sunspots now are connected through solar flares and solar wind to geomagnetic storms. So now it's important that we watch for sunspots. And what we've noticed over the last couple hundred years is that sunspots occur in 11-year cycles. So if we look at the peaks occur every 11 years. So right now we're at a solar minimum, but we could be at a solar maximum soon, which means that we could be, we need to be prepared for possible increase of solar storms. So the 11-year cycle is kind of important to watch. Okay, so we've explained sunspots, solar flares, and solar winds. We've related these events with auroras and power disturbances here on Earth. So now we're going to explain, how do we know what really happens in the sun, and how do we know that it goes through the process of fusion? So we can tell a lot by a star by looking at the light, and specifically taking white light that comes from our sun, or really any star, and putting it through a prism. And when we do that, it separates the light out into a rainbow, but this isn't very spread out. So if we put it through a prism that really stretches it out, we would get a rainbow that looks like this. And so this is in all rainbows. We just can't really see it because all the colors are so close together. But what we can see is there's these dark bands, and these dark bands are there for a reason. They are there because elements in the star are absorbing some of the energy, and when they release the energy, they don't release all of it. And so some of the energy gets absorbed. And so each of these bands is related to an element inside the star. And if we know the signature of the element, then we can determine what elements are in it. So here are the light signatures from several different stars. And you can see that there's some similarities, but there's also some major differences. And the differences in the bands are connected to the elements and the temperature for each of those stars. So this is the vertical bands that I was referring to. So hydrogen has a very unique signature. It's got 4 bands, one in the red, one in the green, one blue, and one in the purple. And they occur in very specific spots. So if we see these vertical bands in these spots, then we know hydrogen has to be in the star. And hydrogen isn't the only element that's got its unique signature. Every element has its unique signature. So we can compare the signature of a star to the elements that signatures that we know, and we can pick out the elements that are there. So why are there different elements inside of a star? So stars are big and they have a lot of gravity, and we know they have a lot of gravity because it's big enough that the Earth could actually revolve around the sun. It's influenced and pulled in by its gravity. So we know there's a lot of gravity, but there has to be something inside the star to overcome that great gravity, or else it would just collapse into a black hole. And so the force that's working against gravity is the force of fusion. So we know that nebulas are clouds of hydrogen mostly, and other things, but it's mostly hydrogen. And so we know that that's how stars form. So if a star with hydrogen gas goes through the process of fusion, then that is one explanation for how we could get all of the heavier elements. Now this is a more accurate picture of what happens than what we did in class. In class we took marshmallows and represented those as protons, and so we would take two hydrogen atoms or two marshmallows and smash them together and get a helium, and so on. In real life it's more complicated than that, but it's essentially the same idea. We take smaller things, we smash them together, and we get bigger things. And so if we start at the top here, we take two protons, smash them together, we get something bigger, and then we take that with another hydrogen and smash them together, we get something bigger. So it's a little more complicated than what we did in class, but it's essentially the same idea. So through the process of fusion, not only do we get heavier and heavier and heavier elements, but we also get a release of energy every time two atoms are fused together. So this is a periodic table that's color-coded by where the elements came from. So hydrogen was formed first after the Big Bang, and for a very short time it was hot enough for some of the hydrogen to fuse into helium, but that didn't last for very long. So we got a little bit of helium, and that's it. So the rest of the elements, or I should say most of the rest of the elements, are made from large stars when they go through the process of fusion. And then there's some tricky things that happen, but essentially iron is kind of the limit under a normal process of fusion in a normal star. And then pretty much everything after iron is made when stars explode in supernovas. Now there's obviously some exceptions. There's lots of green ones that are below iron, but for the most part we'll just say that everything after iron is made in supernovas. And then the purple ones don't exist in nature at all, and we can only make them in a laboratory. So this is an area of current research in physics to try to figure out why these don't exist in nature and why we got the elements and the types of elements that we do have. So this is a chart of the abundance, and so we can see the most abundant elements in the universe, or really here, this is supposed to be here on Earth, we're most abundant up to iron. So these are the most common elements in the universe. When stars exploded, they spread their elements throughout the universe, and that is one explanation for why the top of the periodic table is so abundant here on Earth, and everything below iron is pretty rare, because it didn't get made as often in large stars, and it only got made once the stars exploded, which obviously needed to happen for those elements to get to us, because the elements that are currently in our star can't also be here on Earth. So all the elements here on Earth came from previous stars that exploded, which is kind of cool. So that is the end of this learning target.